invitation, and it's really a pleasure to be in this specific event. So if you are ready, then we can start the proceedings.
Yeah, I'm ready. I'm ready.
Okay. Shantanu, it's over to you.
A very good afternoon to everyone. Myself Shantanu Dilip Devle, and I'm MTech student at IIIT Hyderabad. I feel honored to extend my warm welcome to all the attendees. On behalf of IAStructE IIIT Hyderabad student chapter, I want to take this opportunity to welcome our honorable guests, faculties, participants from the academia, the research fraternity, industrial professionals, and all the students who joined this webinar on the topic, India's infrastructure towards resilience, tackling dilapidated structures with research-driven strategies. On behalf of I would like to introduce our keynote speaker, Dr. Aditya Singh Rajput. He is currently working as an assistant professor in the Department of Civil Engineering at IIT Ropar. He did his master's in the building technology and PhD from IIT Roorkee. His research focuses on developing durable, cost-effective solutions to enhance the lifespan of both modern and heritage structures. With expertise in corrosion-induced deterioration, seismic performance analysis, and retrofitting of composite materials. He also worked on low-carbon concrete solutions through carbon sequestration and waste valorization. Dr. Rajput founded the Center of Excellence Vernacular Architecture Seva at IIT Ropar. Dr. Rajput also has a great experience in the field where he was working on the significant heritage sites like Sri Kashi Vishwanath Temple in Varanasi and the Town Hall building at Kolkata. His work bridges academic research with practical applications to improve infrastructure resilience. This is a brief introduction to the speaker. Now, before we start the event, a small announcement for all the participants. If you have any questions, doubts, or clarifications, please do type your queries in the chat box only. We will have sufficient time for the discussion at the end, where Dr. P. Praveen Kumar Venkatrao, faculty advisor of the student chapter, will be the moderator. Now, without any further delay, we would like our speaker to speak. Sir, over to you.
Thank you, Shant. Yeah, it's over to you, Dr. Rajput.
All right, thank you, Shantanu, for your introduction, and thank you especially to Dr. Praveen for inviting me, who also we are a very good friend as well, apart from being
pleasure,
professionally colleague. And apart from it,
you're not audible, Dr. Rajput.
am I not audible?
Yeah.
Hello?
Yeah, the voice is coming very low, actually.
Okay, let me just see. There might be some problem with...
Now it is fine. Now it is fine. Yeah.
Okay, so I'll try keeping my volume slightly up.
There was an audio fluctuation. Yeah.
Okay, so please let me know if any technical glitch arises in between, because I may not be knowing it.
Sure.
With that note, today's talk I'm going to give on a very important topic which pertains to my research domain, but at the end it affects all of us, which is India's infrastructure toward resilience, tackling dilapidated structures through research-driven strategies. So here, what I'm trying to give you a context of this presentation. So I'll be giving you, based upon my experience over the field, how the dilapidation or the deterioration or the aging in the structure, particularly in India, is taking place, and what possibly we can do in order to avoid these premature failures or aging phenomena in the structures. So I'll be starting my presentation with some very uncomfortable truths that we quite often hear in news or in print articles, which is related to collapsing of different structures, not because of earthquake necessarily. Even without earthquake, under the regular service loads, we quite often hear that the structure got collapsed and so many people died or injured. Now, these type of incidences takes place obviously in a distributed manner throughout the year and becomes more prominent during the monsoon. So therefore, we hardly give as a general public any attention to it, though we moan, we feel bad about it, but apart from it, we move on. But as a civil engineer, it is our responsibility to look toward the depth of these type of issues, because they are actually causing a lot of problems in terms of economy as well as a loss of life. So I'll be giving you some statistical analysis that I have done as well. So Indian homes are India basically homes one of the largest dilapidated housing stock in the world. Dilapidated basically means one which is in bad condition or are not fit for the occupation, but still they are being used in India. In every monsoon, collapsing of homes are deadlier than the flood itself. So in India, that's an irony that during monsoon, there are more people dying because of the collapse of houses. And I'm sure that you must be hearing these type of news quite a regular basis. So basically, our structure does not even need a natural disaster such as earthquake or cyclone or landslide or fire. They are collapsing under their own service loading conditions for which they have been designed for, and there is a good amount of factor of safety also has been given, but still this is the scenario. So in this scenario, as a civil engineer, the question that should arise in our mind is that do we acknowledge the magnanimity of this problem, because they are happening in pockets. So sometimes we miss the magnitude or the gravity of the problem. Second, that even if we acknowledge this problem, what is our preparedness? What we can do as a student of civil engineer or as academician, as a researcher or someone who is working in the industry, what should be our contribution to this domain? So with the help of statistics, I would like to give you a brief about this problem. So basically, I have analyzed the National Crime Record Bureau's
Dr.
data.
Rajput, sorry for the
Yes.
interruption. Your screen is not visible. Have you shared the screen?
Yes, is it not visible?
No, we can
I'm
only
sorry.
see you. So I was wondering, initially you're giving an overview
Okay.
and then we'll start.
No, I'm sharing my
Yeah,
screen, sorry.
Yeah, now we can see. Yes, thank you.
Okay, so is it visible now?
Yes, yes.
So
It's
basically what I was talking about is this slide over here that you are seeing, which is related to these unfortunate incidences that quite often occur in different parts of our country, and some important points such as during the monsoon we loses more life because of the collapse than the flood itself. And as a civil engineer, do we even acknowledge this problem, the magnanimity or the gravity of these problems, and what is our preparedness with respect to the? I hope the screen and my audio both are good right now.
Yes, it's absolutely fine.
So now with that, I would like to now switch your attention to the statistical analysis that I have done in order to get an idea about the magnanimity of this problem. Basically, I have taken the help of NCRB, that is National Crime Record Bureau's data in the period of 1995 to 2015. The reason why this period has been chosen because after 2015, NCRB stopped publishing data in this particular context. So we do not have data as such specifically for the number of incidences for the structural collapse and number of injuries. And all the data that I'm showing right now does not include the loss because of the earthquake. These are the data which primarily is because of the collapse of structures under service loading conditions. So you can see in this period, we lost approximately, the total number of incidents that we have seen was around 26,000 or more than that in these 20 years. Out of them, a majority comes from the residential housing stock, followed by commercial and then bridges. Number of injuries that were recorded was up to 11,000 or more. And these are major injuries basically which comes on record. And the number of deaths that are recorded are more than 28,000. So in these 20 years, we lost approximately 29,000 people. leave aside the financial or other losses that the country or the society suffers, but only the life of humans we have lost during these incidences is more than 28,000, which basically amounts to 13,000 cases per year, 1,300 cases per year, or equivalent to, which is basically 1,450 deaths per year that we are losing just because of these collapse, though they are happening in small pockets and therefore does not come into our attention all the time. Apart from these losses that we are suffering, we are also losing billions of rupees as a for different type of amount that the government need to spend in order to compensate it, and the loss of infrastructure and all those things. So basically, with these things in mind, achieving the sustainable growth aspect is a major problem. And when we include the earthquake also, so earthquake alone caused approximately 14,786 deaths in this duration of 20 years. That is equivalent to 821 deaths per year. But if you will just exclude the Bhuj earthquake, which happened in 2001, this number comes out to be very low. If you will see only 60 deaths per year. I'm not saying that earthquake is not important. What I'm trying to say is that the emphasis that is given for the earthquake during the design, and we in our subconscious as well, we consider earthquake as a major natural disaster, which actually it is a major natural disaster. But in terms of losses of life and number of incidences, if you will see, the loss that we are suffering because of the gravity loading conditions in itself is a very important and huge numbers, if you will see over here. So that's the importance of this particular domain. If you'll see the status with respect to different states of India, you will see it is directly proportional to the population as well as the number of modern or high-rise structures that are present. So the more industrialized the state is, or more populated the state is, the number of cases of collapse as well as deaths are higher. So with that note in mind, which I hope was able to give you an idea about how serious this problem is in terms of its consequences and amount. I have had the opportunity to visit more than 50-60 structures across India. Some of them are listed over here. So within these structures, the structures as young as 5 years was also within my list, and the structure as old as more than 200 or 240 years is also within this list. Obviously, the structure which are older than 100 years, often we get them in form of either stone masonries or normal brick masonry type of structures. But the modern structure that I visit primarily are of reinforced concrete type of structure. I hope you are aware about the reinforced concrete structure. What does that mean? So this is the list of structures. Now within these structures, I would want to opt for only 5 type of structures, and I want to give you a brief of these case studies in order to give you an idea that how does this problem of dilapidation or aging or premature aging looks at the site, and what could possibly be the reasons. So these 5 structures, I have hidden the identity or the project details, but just to give you a case study or idea about it, there was a case number 1 is about a commercial building, which is G+3 story, a normal building with an age of 8 years. Here you can see that's the building, which looks quite okay. When you see it from the elevation or outside, it's just a 8 years of age, so hardly it has lived its life. But some of its portions started to show severe corrosion levels. If you will see over here, the slab reinforcement is popping out because of corrosion. There was a severe de-stresses noted across these structures, and some of the portions were even coming, life threatening. So in order to save the life of the occupants, we had to order, first of all, this entire building to be evacuated, and then a detailed investigation was done. So for the detailed investigation, it was an interesting case for us as well, that a building as young as 8 years, how come such amount of corrosions can occur in a building? So we started to dig or we started to examine different sound looking places as well across the structure, and we got to know that even if the surface of the column or beam or any RC member seems to be fine from outside, When we drilled till the reinforcement level, we got to know that it has severe reinforcement at the reinforcement level. That was true for all the cases, be it column, beam, slab, different locations, different floors, everywhere. So it was certainly a case where there was a corrosion going on constantly in the reinforcement. So a question arises that what could possibly be the reason for such type of distresses? Because if you see the distresses, sometimes they are located near the wet areas or near some locality within the structure, and rest of the structure seems to be fine. But here the reinforcement across all the locations were corroding, and therefore we further investigated with the help of different non-destructive testings, chemical analysis, and we got to know that the primary reason for these type of or in this structure was basically the poor quality of water. That means the water that was used during the concrete making and during the curing, that water had high sodium chloride or NaCl concentration in it, and therefore it was not suitable for concreting, but it was used because in India, unfortunately, we give the least importance to water. What we are drinking is still our concern, but what is being mixed in the concrete is not at all our concern. And no one can think of that a building costing approximately 150 to 160 crore can be considered to be completely damaged or not fit for use just because of the poor quality of water, which is actually free. If you just give some emphasis to this aspect, it would not happen. But unfortunately, that was the main reason behind this particular distresses. And because of this, this entire structure was prone to was considered to be highly prone to corrosion. And therefore, the suitable measures after that was taken. So that was the case one. I hope you got an idea that where they made a mistake or where we are making a mistake. Number one. Number two, another case, a hospital building, a very, very important hospital building for India, located in a very important region, G plus 7 story, age more than 40 years. And the building comprises of a basement and basement and ground story and then plus 7 story. So you can see the weight that is coming over the columns at the basement is reasonably good. So when we were asked to visit the basement portion of this building because ground to 7 story was fine because they were operational, they were largely fine. There was no major de-stresses at all. But when we visited the basement, which the hospital authorities never visit because they consider that since this portion is not being used by the hospital, it is not our concern to visit or see the health of this structure. So when we visited, this was the condition of the basement. You can see the water accumulation all along the floor. It was around height, 1 or 2 feet of water was accumulated. It was there from I don't know how many years, but definitely it resulted in deterioration of the entire slab portion of the basement. So in the third figure over here, you can see that how the slab has been damaged to what extent. And that was merely because of the ignorance of the authorities or the maintenance team over there who was responsible for the maintenance. And upon discussion with them, the argument that they were giving, since this particular portion of building is not used, it is hardly maintained. There's no amount to maintain it. But you all as a civil engineer can understand that if your basement is not healthy, how the other buildings which are above it or how other floors which are above it would be healthy. So basically, we again cleaned it up and then carried out entire investigations to examine the amount of corrosion, the aging potential. Everything was done, and basically it was figured out that the column and the beam particularly were found to be in very good state. Though these beams that you are seeing over here were corroded, but the primary beams that are going over here, as you can see like this, they were found to be still. See, this structure have never been maintained at that particular portion of the building, but still the column beams were constructed to be of very good quality. They were still doing pretty much good. They were not corroded. The readings with respect to NTT analysis potential, everything came out to be within the range. But obviously the slab portion was completely damaged. You can see over here. So if I try to conclude, the main problem in this particular case was primarily the ignorance of the maintenance team or the poor maintenance, which again is a very prominent case in India. You will quite often find that particularly the government building stocks are not being maintained properly. And within that structure, particularly those areas which are not visited quite frequently are in deteriorated. It could be a terrace, it could be chhajjas, it could be some wet areas, store areas, basement, something, some areas which are not having any functional use as such for the building, they are ignored and therefore the deterioration takes place from there. So that was a case of poor maintenance. And again, very important reason and very common reason in India if you go on the site. Third case is again an institutional building, which is a Jeep or four-story building as young as 5 years, just newly constructed, hardly handed over, but the authorities started to notice a problem that this building was having seepage throughout the year. Throughout the year, it was having seepage issues from the expansion joint. There was a water dipping continuously. Now, that was a mystery for them because there is no piping going on, there's no plumbing involved here, there's no wet area nearby, but still, throughout entire building at the periphery and all the expansion joints was continuously dipping. So this became a major problem because this building was a very important building, and therefore it was mainly constructed with a fund of 350 crore. And you can understand that these type of problems, if they are occurring, VIP visit or anything is coming over, it obviously cannot be done in these type of scenarios. So the authorities which were responsible for managing it were contacted us, and then we visited this site particularly. You can see the water was dipping continuously all along the periphery, and which was actually causing the structural members started to de-stress, because obviously if there will be a seepage throughout the year, there are very high chances that the RC elements, be it beam, column or slab, will start to corrode, and that's what was going on over all along the structure. So upon doing all the investigation, everything, the main problem that was done or that was found in this particular structure, that the quality of construction is good. The maintenance is also fine. The only problem was the waterproofing treatment that they did to the terrace was not good enough. So what generally is done is that at the terrace level, thermal insulating puff is given in order to provide thermal insulation to the lower stories, and also then a waterproofing arrangement is done. So in this place, what they have done a thermal insulation puffing, but after that, the water proofing treatment, basically a channelized polymer composite layer is provided in order to channelize if there is a water seeping through the RCC slab. It will basically be going toward the slope. That's what it is supposed to do, but that was actually not provided. Maybe it was missed, or maybe it was intentionally missed. But because of that, what was happening? The water during the rainy seasons used to percolate through the PCC that was laid above the insulating puff, and it was basically being stored in this insulate because it's like a puff of 6 inches. So it acts like a reservoir which can hold water, a good amount of water. And then this water used to slowly seep through all the downward sloping areas, be it a joint or be it on the periphery, wherever it was finding its travel, it will go there and keep on seeping in a very slow rate, and therefore you will find the seepage throughout the year in the areas where it is not supposed to be, because there is no plumbing as such. So in this particular case, I can say that the build quality was good. The maintenance team was also very sincere. They were doing good. The material was used to be fine. But just because of one mistake, that while doing the waterproofing, they missed the waterproofing in itself, and they provided thermal insulating puff followed by a thin polythene layer and followed by a 6 or 8 inches PCC for the sloping. So that's what they have done. And because of this, the main reason here was the poor waterproofing, and because of which this entire slab portion, if you will see toward the terrace, this entire PCC of 6-8 inches was removed, and it was cost around 4 to 5 crore to them to just repair this once again. So that was a problem, but it's good that the problem was identified in the beginning of its age, and therefore no much deterioration to the building has caused. And after successful replacement or doing the waterproofing properly, the building is now doing pretty good. But still, it is a case. If you will, it will observe that the seepages through the terrace is very common phenomena in India. We do not take care of the slope or the waterproofing very seriously in normal housing as well. Case number 4, again, a hospital building. It's an old building constructed by the Britishers, so during the Britishers' time. And it was a random double masonry building, G plus 2 story, but originally it was constructed as G plus 1 story building. The ground story had 20 feet height. So it was basically a heightened story and then followed by a normal height, that is 11 feet height of building. So you can see this is the ground story over here. That was the first floor. Then this first floor, again, second floor was added later in 2011. So what happened after construction of this additional floor over here, the ground story started to show some cracks randomly here and there because the building was made with the random rubble masonry. So the patterns of cracks does not follow a uniform pattern here. And therefore, since it was a very important regional hospital, and primarily responsible for the for childbirth and all those activities were taking here. So basically, it's called Janana Hospital. So the the risk to the infants or the risk to the mothers was very high because this plasters was popping out continuously, and it there were some incidences where it fell over the some instruments or over the floor, and therefore it was suggested to first evacuate it because it was not seemingly safe. The things were not looking good in the ground floor story. And when we did entire investigation, structural analysis, and everything, we got to know that the building was primarily behaving or having these distresses because there was an additional construction or overloading was done. So again, it's a very common phenomena in India. You will quite often find that people do build additional story without considering the strength of lower stories or the foundation, and that actually causes problem to the entire building because if your ground story is not behaving good, obviously there's no point of having the so second story was constructed in 2011, but you cannot say its life would be 50 years because your ground story will not live for 50 years in this scenario. So that again is a very common phenomena in India, which results into structural distresses, collapse, and losses, but we do not realize where we are making mistake actually. So in this particular case, the main reason, main culprit, what additional construction or overloading, I can say. Obviously, instances of poor maintenance and lack of hygiene was noted and they were reported as well because being a government setup, as I said, maintenance is a major challenge. So typically those areas of the building which are not functional or which are not directly used, they are ignored. But we need to understand that building is a unique entity. You need to understand that every portion of it has to be remain safe and sound in order for the other members to remain safe and sound. So that's what a civil engineer need to understand. Maybe others may not, but at least we should understand that. Case number 5 is a positive hope. So this was a building which I visited in Mauritius. Its age is more than 50 years. Year of construction was 1968. So when Mauritius got its independence, this building was used to be the only multi-story building in their capital, Port Louis. It's a G plus 7 story building constructed by an Indian contractor, designed by an Indian company, and constructed for an Indian company. So basically, this again is a commercial building, as you can see over here. We were asked to visit it because they have a rule of doing this routine checkup and maintenance thing. So we were asked upon its completion of 50 years that please visit and have a look of it or examine it. If there is a problem, please do suggest. We did a detailed investigation to this building. So this building had a feature that it had on the elevation. These fins that you are seeing are basically they are not structural element as such. So they are primarily the fence which has been given to give it architectural look or elevation to it. So these fence were obviously found to be deteriorating here and there, and that too in a mild or moderate range, not severe. But the structural elements of it, the beam, the slab, the columns, were found to be in very good conditions. I mean, we tried digging into the reinforcement level at various locations, and we were surprised to know that the bars, the ribs on the bars, the stirrups, any type of reinforcement that has been provided in the structural elements is very good, in very good state. The plaster that was provided in this building in itself was of very good quality, that we find it very hard to chop it off, which shows that the plaster here actually add a layer of durability to the structure. Whereas in India, unfortunately, we generally utilize this plaster to hide our flaws. So if there is a honeycombing in the concrete, we'll do plaster and everything looks smooth. The quality of that plaster also is not good enough. If you will hammer it, it will start to come out. So here, if you will see the quality of plaster, the quality of concrete, the quality of construction, the quality of materials, everything was great. It was very good. It was doing great after 50 years. It was obviously, we appraised the building. We noted that some maintenance is needed in these elementary or the elevation elements, that is those RCC fence. But apart from it, the entire building is doing great in terms of its health. There's absolutely no problem for this 50-year-old building. And again, I would like to repeat that this building was constructed by an Indian, for an Indian, and designed by an Indian itself. So there was absolutely no maintenance, very good health. And there are very few cases when you will actually say this in your reports that the structure is actually doing very good in its present state. So with these 5 cases, I have just tried to give you a glimpse of where we are going wrong, or what are the common mistakes that we are committing. Sometimes a selection of wrong material or an ignorance to choose the right water can be the reason. Sometimes overloading can be the reason. Sometimes poor maintenance or ignorance again can be the reason. Or sometimes some basic flaws during the construction, such as wrong waterproofing, can also be the reason. So whenever you are going to visit a site for a structure to do its auditing or assessment, be aware that reason can be anything, and every structure has their own story to tell. So you just need to be objective about it, but you need to also have some of these pictures in your mind, that what could possibly be the reasons. So now, what are the consequences in terms of their structural response? So with that, I'm switching on to now my research objective. But before that, just to summarize, my summary of the field work says that there are 3 stages for a building it's in its life. First is pre-execution, where we do survey, planning, design, and all those things on paper. Second stage is execution, and third stage is post-execution, where maintenance comes into picture. So pre-execution obviously have a very low error possibilities. It's not that we cannot go wrong at this stage, but we can say that the probability of going wrong is very low, because everything is being done on paper, and therefore all the checks, all the design guidelines are being followed here. But still, obviously, because of the wrong considerations, we can go wrong. But the high error possibility lies in stage 2 and stage 3, where because of the wrong material or substandard qualities and all those things, we can certainly make, there are various reasons we can go wrong, and therefore our structures can suffer in this particular domain. So be careful in whichever execution or whichever stage you work on in the industry. Just see if the structure is showing some signs of distress. Try and attend them at the earliest stage possible, in order to avoid, as we did in that structure which I have showed you for waterproofing. Now that structure is doing pretty much good. But the structure which I showed you for wrong water they have used, that structure unfortunately either need a very high maintenance cost now, or it has to be demolished. There's no other option. So with that in mind, let me now switch on to, let me now just conclude whatever we have done. So with that, I'll say for the dilapidated structure, or to make our structures resilient, we have basically 2 options. One is, for new structure, what should be our approach? For new structure, obviously, we need to utilize the latest materials that are available, which are less susceptible for corrosion. If I talk in terms of RC structures, we need to follow the guidelines. We need to obviously make sure the quality of our construction material, everything remains good, and most importantly, the maintenance part should be done sincerely, obviously, for new structure. So material becomes a key word here. For existing structures which has already been constructed, which are already suffering, which already have some type of de-stresses in them, choosing or designing innovative repair strategies is the only solutions. When I say innovative repair strategies, that means this would be feasible in terms of their economy as well as their applications. And that is where actually my research is primarily focusing on, that is to assess the structural response of a structure which is already existing and then design if there is some gap in their performance. So with that, I would just like to brief on the problem that I am trying to attend. Dr. Praveen, if I am going out of time, please let me know, है ना? 5 minutes before, so that I just
Sure.
find.
Sure. Okay.
Yeah, so this is a typical structural frame for a building. You can see over here, it may have foundation, column, beam, slab, and all and these are primarily the RCC elements. Sometimes here wall can also be there. Within that, I have selected column, though all the structural elements that you're seeing are important. Columns becomes of prime importance because they are responsible for the overall stability of the structure. When I say that, I mean if a beam in a local area, if that fails, basically it would result into local failure of that area. But if a column fails, it may result in the collapse or progressive collapse of entire of your structure. So basically, failure of a column cannot be seen in isolation, and columns are sometimes considered to be the most deteriorated portion of the buildings that I have seen in my field visits as well. So here you can see some of the columns where there is a corrosion in those columns, and the rebars have been corroded to different extent. And when these columns, which are already subjected to axial loadings, when they are also subjected to seismic events, which is basically a lateral form of loading that is applied over the columns, how they are going to behave. So that is the loading scenario generally the columns are subjected to during earthquake, though in a normal condition, they'll only be subjected to axial conditions, axial loadings, and if there is a eccentricity or something, there will be some movements as well. But when it comes to earthquake plus gravity, that's the worst kind of loading scenario generally a column will be subjected to. So with that, we had two questions in mind. Question number one was, what is the effect of corrosion on seismic response of RCC columns? So basically means a column which has been designed for considering the full capacity of the rebar. If that columns gets corroded, how it is going to behave, or what would be the reduction in its seismic response. Second, if we know the amount of seismic response which is lower than the desired one, how can we bridge this gap with designing suitable retrofitting strategies? So how we can restore the adequate seismic performance? That's the question number two. With these questions, the present discussion will go on from here now, which is basically my research work as well. So in my research, which was primarily experimental in nature, I prepared a different type of column specimen. So you can see over here a column footing assembly that we have prepared. We constructed around 17 such columns, which different configuration. So in second figure, you can see over here, I am designating them as generation 1 columns, which is basically the first generation of columns, which was being constructed in India and across the world when the seismic ductile detailing guidelines was not into picture. In India, we received our first seismic ductile guidelines in 1993 with the code 13920. But before that, if you will see, so I just want you to focus over this reason over here. So if you will see, the spacing of the lateral reinforcement was high. Obviously, this spacing over this region will also be high. It would be around 300 mm center to center. But I have kept this deliberately strong because I wanted my failure to be concentrated in the potential hinge region. But so that's what the characteristics you need to record. Okay. And similarly, if you will see in the potential hinge region in generation 2 columns, which follows the latest seismic guidelines, if you will see, the spacing of the reinforcement reduces to 75 mm from 300 mm. Okay. So basically, the generation 1 column seems to be relatively having lower amount of reinforcement in their lateral direction. The amount of longitudinal reinforcement was kept to be same because we wanted to examine the post-peak response of the column, and which is primarily dependent on the confinement that is given to the column. So now we are entering into slightly technical side of it. Basically, the amount of lateral reinforcement that you are going to provide would determine how the column will behave when it is reaching its peak. So post peak mein how it will behave, that's what is governed by primarily the amount of lateral reinforcement that is provided. So generation 1 columns seems to be slightly on a deficient side, whereas generation 2 columns seems to have more amount of lateral reinforcement, and therefore they are generally desired to behave in a more ductile or better manner with respect to the seismic response. With that in mind, I have prepared a total of 17 columns, out of which the 10 columns were generation 2 columns and 7 were generation 1 columns. Generation 1 basically means under confined, which has lower amount of confining reinforcement, and well confined means which has adequate amount of confining reinforcement. So generation 2 or generation 1, or if I call it as well confined or unconfined, they are basically the same thing. Okay. So out of 17 specimens, 4 were basically the columns which were not corroded, which were in their sound state. 6 were corroded, and remaining 7 were corroded and then retrofitted either with UHPFRC, which is a composite, which is a advanced concrete type, you can say ultra high performance fiber reinforced concrete, we call it. And then the second material that I used for retrofitting was glass fiber reinforced polymer, or GFRP we call it. So there was different stages of retrofitting that we have carried out based on the response that we got from the previous column. So that's how we proceeded. This was the testing setup. This is the actual picture of the testing setup and the amount of the instrumentation that has been done. You can see my primary focus, as I said, was on the potential hinge region, and therefore all the instrumentation was provided here in terms of LVDTs in order to record the rotation, the curvature, experimental, everything. The lateral load was applied at this point, which is at a height of 1500 mm from this face, which makes the lever arm at this point as a 1500 mm. Total height of the column was 1800 mm. There I am applying a axial load, which basically simulates the actual gravity load that will be acting in a column during the event of earthquake. Okay, so that was the loading condition and instrumentation. These are the 8 different parameters that I tried to calculate. And again, I would like to repeat that I was examining primarily the seismic response here, because that's the most critical type of response that we generally need from a column. Obviously, if a building or a column is good for the seismic response, that would be obviously good in their service conditions as well. Okay, so these are the load deflection, moment curvature, and 8 different performance indices that I calculated for each of the 17 columns so that we can compare them. Now I'll be moving quickly. So basically the objective 1 was about comparing the generation 1 to generation 2. No corrosion involved here. Objective 2 was examining the effects of corrosion on generation 1 column, then effects of corrosion on generation 2 columns, then the retrofitting and its efficacy examination for generation 1 column, and then the retrofitting and efficacy or quantification of its efficacy in the objective number 5 for generation 2, which is well confined column. So I'll be only discussing about this 5th objective in this presentation just to save some time. So again, in the 5th objective, I had a total of 7 specimens. One is 0% corrosion. Again, the objective 5 was for well confined column, that is generation 2 columns. That means the columns which has been designed as per the latest Indian design guidelines and therefore are considered to yield us desirable seismic response. But what happens when they get corroded? Because code does not say anything about it. We need to quantify this response, that if it was supposed to give this performance, now how much it is giving. Okay, so 0% corrosion basically replicates or represent the control column, which will give you an ideal state. That means this much of ductility should be there, this much of energy absorption or energy dissipation should be there in a column. This should be the load capacities and all those things. So 0% is a control column, and all the others will be compared with this. So then the second column was having a 10% corrosion, 20% corrosion was the third column. Then there was retrofitting series, so 10% plus retrofitting, 20% plus retrofitting. And if the performance did not come out to be in a desirable manner, then I'll enhance the efforts on the retrofitting side. So apart from having UHPFRC, now I'll add one more GFRP layer and then 2 GFRP layers. So that's how I basically started to proceed. Now this is the steps, or the picture shows different steps of the construction. So cage preparation, then we attested different strain gauges over here, if you can see it. Then it was prepared or casted in a mold. So you can see over here, the stuff, the column, everything was planned in a way so that we can easily construct it, because it was a full scale structure. So therefore, then curing was done. Then after curing, they were cleaned out again. And we did a GFRP wrapping over here. Again, as I said you that in this reason, we provided closely spaced stirrup in both generation 1 and generation 2 columns. We also retrofitted it earlier. I mean, we wrapped it with the GFRP just to make sure that this reasons remain always extra strong. This reason obviously remains strong because of its size. So this reason is the one where we'll notice or quantify all the failures. Now it is the reason why we are focusing over this, because that's the potential injury reason. That's where we are expecting the failure to occur. That's where the field studies have suggested that this is the zone of failure. That's the zone of failure where the failure actually occurs on the site. So therefore, we are only focusing our test length over this reason of 800 mm, which is this total length. So if you will see is 800 mm. This entire 1800 mm, this is 800 mm, okay, which is the test reason. Then we'll prepare it for corrosion. Then the corrosion was started. You can see over here, sodium chloride solution has been given. These are external DC machines. There's this entire setup for this external corrosion that is given, which is called impressed current-based techniques. Then after corrosion, you can see over here, this region has suffered significant amount of corrosion. These are corrosion byproducts, which you are seeing over the surface of it. Then it was cleaned, cracks were noted, cracks were recorded, all of them. And then it was tested after, so the columns which were supposed to be examined only for corrosion, they were examined after this stage in the test setup, which I showed to you earlier with head actuator and all those instrumentation in it. But those structures or those columns which were supposed to be retrofitted after this stage, they were then sent for retrofitting. So for retrofitting, we removed the cover concrete because that was damaged because of corrosion. We examined or cleaned all the reinforcement that you are seeing over here. Now, after this stage, there can be different ways of retrofitting and their efficacy may obviously differ. We chose to go with a convenient one, which is to restore its cross section with a higher grade of concrete, which had some flexural strength as well, which have some fiber as well. So that we called as UHPFRC. You can see over here, we are pouring it again after applying the molding. And you can see that after pouring, we recovered the concrete, the cross section once again. But now this concrete is basically the UHPFRC concrete stated at the cover. On the core, obviously, it remains the same M30 grade concrete, the normal concrete. So that was my retrofitted specimens. You can see it's neither its weight has increased, nor its cross-sectional size has increased. So there's no increase as such. But at the same time, we have applied at least one layer of retrofitting, which is only using UHPFRC. Now, we will examine this specimen to the same testing setup, and then we will compare it with the normal 10% corroded and 0%, that is the control column, and we'll examine that whether the load capacities are good enough, the ductility is good enough, and all those things with the help of those 8 indices that we have calculated. If the performance was found to be not good enough, we will again cast a column, corrode it to 10%, remove the cover concrete, retrofit with UHPFRC, and now retrofit with one more layer of GFRP. So that's how it has to be, the experimental plan of it. So that's, you can see the retrofitting with the GFRP as well has been done, and then they were tested. So once they are tested, they were demolished. Their rebars in this region were removed in order to visually inspect that corrosion has occurred, what is the pattern of corrosion. Then they were weighed again in order to record the amount of mass loss, which will basically determine the degree of corrosion. So that 10%, 20%, 15% corrosion, which I'm saying actually is a round up amount. So originally the amount can be 14.8% mass loss or 16.2% mass loss or 20.2%. So I am giving it a category 20% with an error of, or with a variation, not error, but variation of plus minus 1% always. So if I'm targeting 15%, it can be somewhere between 14 to 16%. That's what I have done in my experimentation. So this was the entire process or the treatment given to the specimens. Obviously, while we are testing, we again calculated these 8 indices, which I have shown earlier as well. It has ductility factor, stiffness degradation, load deflection response, and all those things. So this is the comparison of all those 7 specimens. This was a control specimen, then 10% corroded, you can see its performance has reduced, then again 20% it has further reduced. For 10%, when we are doing retrofitting with RU means retrofitting with UHPFRC, so you can see its performance has again jumped to almost its the control one. Similarly, for 20%, we can see the response has increased. We again the G1, that is 1 layer of GFRP, and G2, that means 2 layers of GFRP. So the response keeps on increasing and we keeps on adding the amount of retrofitting. Okay. Same goes with other parameters. So here I have compared the backbone curve of those hysteresis response just to give you a visual comparative understanding. Here you can see over here the lateral load or the flexural strength of the column is compared. So the control column, if I assume it to be 1, that means something which I am controlling all the columns with this. That is the normal column, or which has not been corroded, which has been designed as per the latest Indian guidelines. It is supposed to be 117. So that was the flexural strength that I got for a normal column which is not corroded. Then when it corroded by 10%, you can see that there was a reduction of almost 15%. That means now it is only 0.85, 98.9 kilonewton, or which is 85% of the control. Then you can see when I retrofitted this column with only UHPFRC, that's it. You can see the lateral load capacity again got increased to 128, which is even 10% higher than the control column, which seems to be fine, acceptable to us, because we have completely recovered. So even if a column which has been 10% corroded, if we retrofit it using only UHPFRC, we can recover its complete lateral strength or the lateral load capacities. Okay. Then for a column which was corroded to 20%, if you will see the reduction in the lateral load capacity was 49%. So we only got 59.3 kilonewton, whereas it was 117 kilonewton over here. So you can see 49% reduction. Then we retrofitted it with a UHPFRC only. You can see RU over here. Then we retrofitted it using RU G1, that is 1 layer of GFRP and 2 layer of GFRP. So if you will see, just by having RU, that means only retrofitting with UHPFRC, we recovered almost the same strength as it was in the control column. Then the question arises that why we are going for GFRPs. The reason lies in the ductility response. This is only the peak response that I am giving it to you, but the post-peak response also is very important when it comes to having a good seismic response, because that's where we are focusing on, right? So though the load we recovered, so you can conclude here that if you want to recover only load, you can just go ahead with the UHPFRC retrofitting, even if the column is corroded for 20%. But if you will see the ductility factors over here, the ductility factors, it was not recovered. It's the same column over here, which has been retrofitted with UHPFRC 20% corrosion. You can see it's 27% lower than the control. So we had to add extra GFRP layers in order to come to its point. So you can see the increase again or decrease again is neither linear nor in a pattern. So you can see over here, it was 15% reduction at 10% corrosion, and then it was suddenly 49%. So corrosion got double, but the response got triple. Response reduction got triple. Similarly over here, if you will see, just by adding 1 layer, we were able to enhance only from 27% loss to around 21% loss. But when we added 1 more layer to it, you can see over here, the amount of the ductility that we got was almost comparable. So either the increase or the decrease, when it comes to corrosion in itself, it's a very random phenomena. So you can say 10% corrosion, you may have some degree of de-stresses or some degree of reduction in the response, but on 20% could be exponentially lower. Similarly goes with the retrofitting as well. So that's a very random phenomena. You will have to make an idea, some qualitative, quantitative assessment. That's what we are trying to do here. Same goes with the cumulative energy dissipation. So we continued with the retrofitting or continued to increase the amount of GFRP until we received acceptable lateral load capacities and acceptable or comparable ductility factors and energy dissipation. That's what the condition was for the retrofitting. Okay. Obviously, we are doing retrofitting just to have a desirable response. That's what we are trying to do. Same goes with the other type of indices. I won't spend much time here, but similar type of trends were noted here as well. A reduction during corrosion, then slowly or slightly increase, and then receiving a reasonably good amount of response in the post-peak or peak response domain. Same goes with the stiffness degradation, axial load degradation, and energy dissipation. So if you will see, these are also very important indices when it comes to the seismic response. If a structure has higher amount of seismic stiffness degradation, that is supposed to have larger drift ratios, and therefore it may be problem with respect to the collapse or other type of structural distresses such as cracking and others. So stiffness degradation is also not expected in the columns, and corrosion actually affects the stiffness or the axial load capacities of your column significantly. These are some of the visuals from experiments. You can see the corroded columns. These are 10% corroded columns. It's a 20% corroded column at surface. You can see the width of the cracks in mm, 0.7 mm, 0.4. So it's basically randomly distributed all across the test length, which is of 800 mm. And these are the visuals of the reinforcement of 20% column. So this is 120% column, RUCC 20%, and that is another 20% column. You can see the visuals of them are very different. Both of them are 20%, but this seems to be more severe. So that's what I was trying to say, that you do not have any control over the distribution of the corrosion. It can be distributed across the entire test length, or it can be distributed more, or it can be concentrated more in a given domain. So you do not have any control over such. Here, if you will see in this 20%, some of the bars got completely lost, and therefore we can always say that the response of the corroded column obviously is a function of the corrosion itself, its distribution, and all those things, which is very random. But still, in order to reach to a conclusion that for an existing structure, which I just showed you during the case studies, what should be our approach? How should we go about? We'll have to somewhere quantify the corrosion that is present in the structure, and then do a retrofitting. And that retrofitting should be validated at some forum. So that's one way of doing it. So we have not only developed a retrofitting strategy which can be applied over the site because it is not adding to any additional weight or the cross-sectional area. And at the same time, it can have very good life ahead because we are using composites, we are using FRP wrapping, which basically avoid the moisture increase and all those things, and therefore the durability of these type of retrofitting systems is very high in comparison to a conventional RCC jacketing or steel jacketing. So these are all the points that I wanted to convey. This is the solution that I am trying to propose here. So that's just a summary of my experimental setup. Again, for different indices, what was the gain and loss with respect to the retrofitting or corrosion. So you can see for generation 2 columns as well as generation 1 columns over here. And some of the important conclusions. So obviously columns with a larger tie spacing or the lateral reinforcement behave inferior in the seismic response. Obviously, we know that the amount of reinforcement is lower, and therefore the seismic response is also going to be lower. When these columns were deteriorated by the corrosion, we saw the seismic response further degraded significantly, and the RC columns, which are actually made in compliance to the current Indian guidelines, they still behaves very inferior when it comes to corrosion. So after getting corroded, their response or seismic response was even lower than the under confined columns, which has not been corroded. So please understand, if there's an under confined column, which on site, if I go, there is a column which is more than 50 years of age, but not corroded so much. And there is a column which is just 5, 6, 8, 10 years old, but severely corroded. So this column would behave even worse than this older column. So it all depends on the amount of corrosion at some point in time. So the response reduces to such an extent, and we have quantified it. Similarly, when it comes to retrofitting, we can say that for UHP FRC alone, if you happen to go on a site, quantify the corrosion, and if you get that the corrosion is close to 10%, you can go ahead with the UHP FRC jacketing itself, but you need to execute it properly, obviously. But you can say that just by using this UHP FRC, I can have a good amount or desirable amount of lateral load capacity as well as ductility. We got to know that. But if the amount of corrosion is more than 15% or in the range of 20%, only UHP FRC may not serve you the ductility, and therefore you'll have to go with the additional GFRP or other composite materials such as CFRP layers with it. So that's what you will have to do. Then again, the corrosion and the retrofitting showed their own effects in the axial load capacities. We got to see that as well. These are some of my publications from the similar work that I have done. And this work is still being continued in a numerical format right now by one of my PhD student. These are some of the publications. So thank you very much for your time. I hope I have not exceeded the time. It was around
No,
40.
you're absolutely bang on time, Dr. Rajput. Thank you so much.
Thank you. Thank you, Dr. Puri.
Thank you. Thank you so much once again for highlighting the challenges, especially in the dilapidated structures in a very nutshell, along with the different retrofitting interventions. Much appreciated.
Thank you.
You can unshare the screen. Now I'd request Shantanu to continue the proceedings. Shantanu, it's over to you.
Thank you, sir, for giving your valuable insights on primary challenges India faces in maintaining and upgrading the aging infrastructure, repair strategies to adopted for deficient structures, safety sustainability for new structures and existing structures approach, and how retrofitting is essential to enhance the structural performance. Now we will take the questions from the participants who are eager to discuss with you, sir.
Okay.
Okay. Thank you, Shantanu. Dr. Rajput, we have a few questions for you. So let me start one by one. There is a question from a participant. Mr. Akbar is asking which non-destructive test shall be performed on the existing structure to confirm the strength.
See, if you are saying it as a strength, there could be strength of concrete if you are referring to. So basically, there are UPVs, that is ultrasonic pulse velocity testing is there, which is NDT type of testing where we do UPV test, and based on this, there is IS code which gives you certain correlation with that. But with my experience, if you would ask, I do not get completely convinced that just by the UPV or rebound hammer type of testing, you can actually get an idea about the concrete. But there's another method which is called the core cutting and then testing it over the lab, which is not NDT but PDT, partially destructive testing. That is even more reliant. So nowadays the practice is that you, in the entire structure, suppose it's a G+10 story building, there's a number of columns and number of beams are very high. We do take core at some locations, and we also perform UPV at those locations as well. And then with the help of those core results and UPV, we first develop a relation between them, and then we conduct UPV at a very high number of places, and then we correlate this data and utilizes that to determine the strength in terms of MPa for different locations. That's about the concrete. But if we talk about the steel, rather steel, not steel, but RCC in itself, we'll have to examine if there is a corrosion that would reduce the strength of an RCC section. If there is no corrosion, only damage in the concrete at a surface, there will be a different method to depends on which strength you are looking at actually.
Okay. Thank you. The next question is, see, the question is relevant to the corrosion of reinforced concrete. The question says, does adding the corrosion inhibitors in concrete will solve the corrosion issue effectively? Corrosion inhibitors in concrete.
Yes. Corrosion inhibitors are there in use. We do utilize it in some of the cases where I showed you. But the problem is with its application and the cost that it involved. So in India, if you'll see, there are movable type of corrosion inhibitors also being developed, which you'll apply at a location and then they will travel to a different location as well. So they can spread as well. So they generally, obviously, they'll quantitatively, if I say, they'll increase the corrosion resistance of your structure. Okay. But it has not been quantified to a conclusive extent yet, that how much and what is the period or frequency of this maintenance that is needed. And cost is obviously a problem again.
Okay. The next question is related to the spacing requirement. Like we have IS 456 and IS 13920, which talks about the spacing requirement with respect to specific locations or regions in a structural element. Now, the participant is saying, instead of changing the spacing, in the confined regions can be considered the high-grade concrete or high-grade steel?
No, actually, see, high grade steel, basically the TMTs that are present right now in market. So it's not a simple steel. You need to understand that we are not the cross-sectional configuration of a TMT is different than a cross-sectional configuration of a high-strength steel. High-strength steel is for a different application. TMTs are basically a cross-section which has a ductile core and very stiff its outer layer. The crust is very stiff and the core is very ductile, and that is because it is meant to behave in a ductile manner post failure scenarios mein. So there we have only up to 500 or 550 or 600 nowadays. So that's the strength of steel we have right now. Confinement basically does not come primarily from the concrete. So concrete generally remains out of option until unless you have a concrete which has a very good tensile strength, which is not the case right now. So closer stirrups is the only possible solution, or if you do not want closer stirrups, you will have to wrap it from the FRP in the external periphery of it, which we do for existing structures, obviously.
Okay. The next question is usually, it is again, the question is related to the confinement itself. The participant saying that usually the confinement is provided for the in terms of the transverse reinforcement, maybe in the form of the stirrups. What will happen if the same is provided in terms of the longitudinal reinforcement? Why confinement requirements are always in terms of transverse reinforcement?
So for that, I guess if you will understand what the confinement is
Exactly.
is basically resistance against the lateral dilation of your column. So that obviously will be always provided by the transverse reinforcement, which is there. Longitudinal reinforcement does not play much role in that. So for confinement, you will have to have something which can laterally resist that movement of your column. So therefore, the lateral reinforcement is needed.
So there is a follow-up question. If the confinement is from the transverse reinforcement, can we provide mild steel stirrups for the transverse reinforcement?
It's a basically play of strength into material. You will have to have both. So if you will reduce the material quality, which is 250, you will have to increase the amount of reinforcement. But you will also have to see that mild steel may not be TMT. So the ductility aspect again has to be examined, which is there in the TMT case.
There is a question which says, this question is referred with case 1 of your study, where the building is 8 years old only. However, the de-stress occurred in the structure is due to the poor quality of water used. Can you throw some light on the quantification of the corrosion contributed by water and the other chlorides in soil and cement, etc.?
See, if you will see during the concreting, there is no role of soil as such. If the aggregates are properly washed, obviously, we do not know. That's what the contractor claims. That because the concrete was coming from RMC. So,
yeah, absolutely.
But when we further digged into the problem, we got to know that there may be two reasons. If you are working near the coastline areas, there may be chances that the contractors are using saline sand, which is sand coming from the ocean, right? So obviously that would have higher sodium chlorides. But in inland areas, a soil or a sand with higher sodium chloride is a lower probability. Similar goes with the coarse aggregate as well. But water in that particular region, the groundwater is having very high sodium chloride concentrations, and therefore we came to this conclusion. Now, quantification can only be done when you know the different factors that are coming in. Here, the chloride infested concrete and its chloride infested water was the main culprit. So that's where we can say that the corrosion that we have shown was primarily because of that only.
Okay, thank you. The next question, or rather query, as we know that over time, aging structures may struggle to support the weight they were originally designed for. So in such a case, what are the effective ways to increase the load carrying capacity?
Yeah, so the easiest way of doing it is there is a step to it. First of all, you need to quantify that how much the response has reduced. So originally, if your structure or your column was designed to take 100 kilonewton load, for example, now you have examined, do your calculation analysis, and you got to know that now it can only take up to 40 or 50, whatever it is. So you have a 50 kilonewton of gap. So for that 50 kilonewton of gap, you need to design the retrofitting. Now designing the retrofitting basically means in present context, we utilizes FRPs very often. And for designing FRPs, if you will see, there are code in American Concrete Institute as well as Canada. India, unfortunately, we do not have right now. But in there are codes which are available to enhance the strength. We can utilize those methodologies in order to design this. These are being done in India at a very large scale now. In fact, I'm doing a project which is 27 stories situated in Noida.
Okay.
That building is actually not having any problem as such, but that's a very important building, commercial building, and there are a lot of international offices there. So now
Okay.
they are saying that since India's guidelines have been revised, the requirements have been revised, you retrofit this structure again. So we are using CFRP for the retrofitting in that case.
Okay. Okay. The next question is, see, if the damage is in terms of removal of cover concrete or the spalling, let's say the spalling of concrete takes place, will it really affect the structural integrity?
See, spalling or cracking are symptoms. The problem is corrosion, reinforcement corrosion. And reinforcements are very important part of the load carrying system in a RC cross section. So if your reinforcement has corroded, that means its cross section has reduced. That means its load capacities has reduced. So it's a very serious problem. Obviously, it's a serious problem. So you will have to take care of the load. It's like if your bones are having lower strength or their strength is reducing. So you can't say that only the skin or the flesh above the bone is actually having a problem. The main problem is with your bones. So same goes with the reinforcement. The reinforcements are very important element of RC cross section.
Okay. The next question is related to corrosion again. Usually it has been observed that during corrosion, the reinforcement acts as anode, right? And if it is made to act as a cathode, by maintaining it as a negative potential, the corrosion process stops. But how effective this process is?
See, that's what I was saying. In that case one, if you will remember, that was our proposal because it was almost a 140-150 crore of investment from the government. Now saying it at a 8 year of age that you demolish this structure is something which is one would be hesitant of saying this, even if that seems to be a possible solution. But we suggested there's a sacrificial anodes were attached. So we suggested this strategy and that was executed.
Okay.
So there are sacrificial anodes are attached, and obviously that works quite well, but the maintenance remains very high. It has been done in Europe and North America. If you'll see, that's a very popular method of safeguarding the structure against corrosion, primarily the bridges. Because of the snowfall, they utilizes de-icing salts and that results into corrosion.
Exactly.
In order to keep it in the cathodic range, they basically provide sacrificial anodes. So it's a electrochemical proposition going on. You are just manipulating it in your own favor. You can do that, and it's effective as well. However, it has to be maintained, and the periodic inspections are needed. So that's a maintenance.
You mean to say that the details has to be properly designed, otherwise the remedy may be worse than the disease in such a case.
Yes. Because the cost of employing it in India right now is very high.
Very high.
You do not have a skilled workforce for that, and at the same time, we need to be very, very careful that the high prone areas may not shift to the anodic side again. So you need to always keep that check always in the building.
So there is a last question. Nowadays, there is a lot of research undergoing in the area of GFRP bars as a replacement for the conventional steel bar. So what do you think? What's the way forward as far as the corrosion of steel reinforcement is concerned?
See, I have also worked over utilizing GFRP bars and beam. And obviously, the main reason why it is being used, and that is, see, first of all, the state of this particular question in itself is quite a mature one, because There are countries which has already developed codes
Yes.
which utilizes FRP bars, and then they are constructing bridges and other structures. The main apprehension about using these FRP bars was primarily the lack of ductility they have. They does not possesses ductility, and ductility is a very important property for having a good seismic response or good post-peak seismic response. So that's the challenge. People are coming up with different innovative solutions such as hybrid bars or having a core of a different than GFRP at the top. So there are different, if you will see now, there's a bar coming over which has a steel-like ductility in the core, but have a composite outer layer.
Oh.
So these type of bars are also coming into picture. So obviously research is going on, but again,
so that the ductility is not compromised.
Ductility is very critical.
Yes.
Just because of the fear of corrosion, we cannot shift to non-metallic reinforcement.
Absolutely.
Because then ductility will be compromised, which if the structure collapses suddenly, then it becomes another problem. So these are being tackled, and there are codes, bridges are being designed completely with the FRP itself, and ductility is primarily being taken care by the steel-based reinforcement. So there are different combinations being done. If you will go, for those structures where ductility is not important, such as for or there where the corrosion potential is very high, that a steel cannot sustain there, people are going with the non-metallic type of reinforcement, such as for pavement, for example. Ductility may not be an issue, but corrosion may be an issue. So in that case, you can use GFRP bars over there. Or for the coastal areas where there is a protective structures are being constructed just to protect the soil erosion or something, ductility may not be the problem, or may not be the first requirement. Rather, resistance against corrosion may be the requirement. So you can go with the non-metallic type of reinforcement. It could be GFRP, CFRP, or any other composite.
So since we talked about the ductility, I also want to clear one more thing. We say that FRP is a composite material which is having mostly a brittle failure, right? Because of which the ductility is not being there. But when you retrofit any structural component with an FRP, either component level or at a structural level, if the failure mode is ruptured, then although the tensile strength of the material is fully utilized, right? But you will not get ductility. But let us say the failure mode is debonding. Although the material strength is underutilized, you will get some deformation. And that is the reason why people say that the debonding failure mode is the governing failure mode in case of an FRP. So how do you look this aspect, especially in terms of ductility point of view with respect to FRP composite material?
That is true. That's true. That's completely true. That if we are, what happens generally, if we can't avoid failure, we try to design the failure, and that's what is being done over here. We do decide the hierarchy of failure. So we want it to be debond so that we get enough warning. So obviously it's a different strategy, but that's an important part. It's like designing an under reinforced beam deliberately, so that the steel fails first, then the concrete. And the RCC design, we have studied that. So it's the same thing. And I completely agree that ductility has to be imparted.
There is another aspect, because whatever strengthening reinforcement or intervention we follow, let us say, for example, nowadays FRCM or TRM composites are taking into its place because of some of the disadvantages of FRP, right? But they are used with some kind of a mechanical anchors. But in FRP, it has been mostly seen that only the epoxy resin and hardener will be used as an organic matrix to adhere to any concrete substrate or a masonry substrate with this composite material. Do you think there is a dire need of some kind of a mechanical anchors if you do not want the debonding failure mode?
Yes, people are using, if you will see at some places, they are using nailing or shear connector in order to avoid these debondings. Now, the material of those nailing or
connectors,
that can be a metallic as well as some other composite. So yeah, but to avoid debonding, obviously you need to have sufficient development or overlapping length. Apart from it, people are providing nailing. So when you'll see the execution, people do provide nailing just to make sure that at the end.
During your experimental investigation, the columns which you have wrapped with that GFRP sheet, so did you use some kind of an anchor, or it was without anchor itself?
No, we did not use anchor. because we provided reasonably good development or overlapping length.
Overlapping lengths. Okay.
Yeah, and we did not see the overlapping or debonding failure. We saw the fibers being rupturing at the very high yield, had the very high drift level. So that gave us a confidence that in this particular case, at least, we do not need it.
Okay.
But obviously on the site, it may be needed in some cases if you want to.
Thank you. Thank you so much for clarifying all the doubts raised by our participants.
Okay.
Thank you once again. Shantanu, it's over to you.
Thank you, sir. I hope all the queries of all the participants are clarified. Now, I would like to call Ms. Shruti Baddipadega to deliver the vote of thanks.
Good afternoon to everyone. I'm Shruti, pursuing MTech in Computer-Aided Structural Engineering. Computer-Aided Structural Engineering at IIIT Hyderabad. It's my honor and privilege to deliver the vote of thanks on behalf of the entire Executive Committee of IAStructE IIIT Hyderabad Student Chapter for this insightful session. First and foremost, I extend our deepest gratitude to our esteemed keynote speaker, Dr. Aditya Singh Rajput, for his insightful presentation on India's infrastructure towards resilience, tackling dilapidated structures with research-driven strategies. Today's webinar has highlighted how premature aging, poor quality of water, poor maintenance of authority, waterproofing system affects the structure development process and stages in it. Effects of corrosion of seismic performance, how we can restore the adequate seismic performance under confined detailing, well-confined detailing, use of QHPF RC, GFRP in retrofitting structures. Moving on, I would also like to express our heartfelt gratitude to our faculty advisor, Dr. Praveen, for his continuous guidance and valuable suggestions throughout the planning and execution of this event. A special mention goes to the IT team for ensuring seamless technical support and to the design team for their creative inputs and logistical assistance. I thank our program coordinator, Dr. Sunita Paliseri, for her continuous encouragement. I also want to express my appreciation to all the participants for their active involvement and thoughtful questions, which enhanced the discussions and made this webinar a collaborative learning experience. Lastly, I would like to acknowledge the hard work and dedication of the entire team whose collective effort has made this event a success. In conclusion, I extend my heartfelt thanks to each one of you for your participation and engagement. We are extremely grateful and look forward to your continuous support in our future initiatives. Thank you.
Thank you. Thank you so much. So here we conclude the entire session. So please stay tuned for the future events as well. Thank you to all the participants and extremely grateful to our speaker. Thank you.
Okay,
Dr. Rajput.
Thank you, everyone.
Okay.
Yeah, I'll take a leave.
Yeah.
Thank you.
Okay.